Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the second in the series on the equilibrium of rigid bodies, and its special focus is on ladder problems. If we have a ladder problem, then it will essentially be a triangle in terms of geometry. There'll be forces acting between the wall and the ladder head, and between the ground and the ladder foot, and there'll also be the weight. So we expect a weight force to be shown halfway up the ladder, though if the ladder were non-uniform, it may be that the problem will specify a centre of mass somewhere else. There will in general be a friction force between the wall and the ladder. The friction force is resisting the ladder's tendency to slide down the wall. And then there'll be a normal reaction, which is the resistance of the wall's attempt to demolish the wall. The ladder's attempt to demolish the wall. And similarly at the foot we'll have a normal reaction from the ground and a horizontal reaction directed towards the wall. That's the friction resisting the ladder's tendency to slide away. So that will be the general setup. Let's now look at a particular context in which that's applied. But before I leave that diagram, may I just point out that I didn't put any letters on those forces, as perhaps you may have expected me to. Putting the letters on is at least as much part of the solution as it is part of the problem. You'll see what I mean by that enigmatic remark in a moment. So let's go to our first ladder problem. A uniform ladder of length 8 meters. It's got one end against a smooth vertical wall. No friction at the upper end. The other end is in contact with a rough horizontal ground. Obviously there will be friction there. The ladder's on the point of slipping, and that occurs when the base is 4 meters from the wall. And we're asked to find the coefficient of friction between the ladder and the ground. So we begin with a geometrical diagram to contain the information given. The ladder is 8 meters long and the foot is 4 meters from the wall. If you look at the angle where my pointer is, then you'll see that it's got a cosine of 4 over 8. That's a half. That's telling us that this is 60 degrees. So we've got the usual relationships between the sides of a 30-60 triangle. In particular, the tangent of 60 is root 3, so this side will be 4 root 3 long. What about forces? There's the diagram I had on the previous slide, except that there's no friction showing. That corresponds to the fact that the question says that the contact between the upper end and the wall is smooth. Well, we'll have to include a weight, so we'll put that on. But this is where a note of caution comes in. Before rushing to put letters everywhere else, we can simplify it. If we resolve vertically, and that's one of the opposite opportunities for analysis that we've got, if we resolve vertically, the two horizontal forces showing won't contribute. So there will only be, for the vertical resolution, a question of balancing the two vertical forces which show. That means this one, the normal reaction from the foot, must be just the weight. The question tells us that the ladder's on the point of slipping, so if we introduce the coefficient of friction as mu, the friction at the foot must be mu times w. Now consider horizontal resolution, another of the tricks we've got up our sleeve, and we can see that this time the vertical forces, the w's, don't contribute, so that leads us to conclude that the reaction at the upper wall, the reaction from the wall is mu w. Now that's made it much simpler because there are only two things there rather than a proliferation of probably 5 if we just put letters on willy-nilly. So from that point then we can consider taking moments, as we've done 2 resolutions. So the sensible thing to do is to take moments about the base. Let's call this A, B, C. If we take moments about A, why do we do that? Because if you take moments there, the two forces at the foot will be eliminated since they go through the point, the fulcrum for moments. So we only need to concern ourselves with the other two. Now the mu w will give us a counterclockwise moment, mu w, and that's going to be times the vertical distance above the foot of the ladder, which from the other diagram is 4 root 3. So mu w times 4 root 3 equals, and then on the right, for the clockwise moments, we've just got the w. Now that will be acting at the midpoint, which is halfway up, so we expect its line of action to cut the base halfway across, so it will be w times 2. Well, that's an equation which will get mu. So let's see that equation worked out. All we have to do is divide by the w's, that's eliminated, and make mu the subject by dividing by 4 root 3. That simplifies to 1 over 2 root 3 on the right hand side, which by use of the calculator gives us an answer rounded to 3 significant figures. So that's our answer to the question. Now notice again I stress that an intelligent use of the diagram to start with makes a big reduction in the work. Let's now look at another problem, a similar one. Again, a uniform ladder of length 8 meters. This time it has a weight. It's against the smooth vertical wall, which means our force diagram will look very similar, and the other end's in contact with a rough horizontal ground, this time with coefficient of friction 0.4. The base of the ladder is 4 meters from the wall, and a man of weight 700 newtons climbs the ladder. How far up the ladder can he climb? Well, let's suppose that he's at his highest point when we reach limiting friction. So the difference between this diagram and the last one will be a force of weight from the man somewhere on the ladder. We don't yet know where. So that's our man of weight 700 newtons. We've also got a weight for the ladder of 250 newtons acting at the halfway point. And if we resolve vertically as we did in the last question, it's easy to see that the reaction at the floor will be 950. Now, since we're assuming it's on the point of slipping, we'll have a friction force of 0.4 times 950, because the coefficient of friction is 0.4. And now resolving horizontally, that same force will be equal to the reaction from the wall. At that point then, we simply have to do a resolution, a moments equation, in order to tie all that together. The unknown, which we'll be trying to find from that moments equation, is the height of the man up the ladder. So let's take our force equation and let's complement it with a geometrical equation introducing the height up the ladder. So that dotted line there, the man is standing where I'm making a blob now. That blob corresponds to the blob on the other diagram. So this time then we'll do a moments equation, and again we'll do it at the point A. It's the obvious place, isn't it? Because that eliminates two forces. So if we take moments about A, we'll have the 0.4 times 950 times the distance up the wall, that's CB on the diagram on the right, which we agreed before was 4 times the tangent of 60. This time I'll do it in trigonometric terms, just for a bit of variety, though I could just as easily write 4 root 3. So that's the moment of that force. We now need the moment of the 700 and the 250. The 700 one is the one that's a bit tricky, as the 700 one has to be times the distance where the line of action meets the ground from A. Well, that will be, given that the man is distant h up the hypotenuse of the triangle, it will just be h cos 60. So it's 700 h cos 60. And then the force, the moment for the 250, the weight, that's 250. The analysis is similar, but this time we know how far the weight is up the ladder. So it's 4 times the cosine of 60. Right, that looks pretty fearsome with the trig in it and all those awkward numbers, but in point of fact it's really very simple, because everything is just a question of numbers or the use of a calculator except for the solitary h, and that's what we're trying to find. So that's really a very simple equation for h. So let's see that equation in all its glory. There we are, that's what I just wrote out on the previous page. We make 700h cos 60 the subject by moving the other terms round. And then we divide by the 700 cos 60 to get h equals from the line above. So now we're as far as that expression. Well, I could just work that out on the calculator, but to save pressing a few keys, I've divided the top and the bottom by the same thing, cos 60. So the sine becomes tan, and the two coses drop out. So we have a simpler expression to evaluate. So if I put the numbers into my calculator, it comes out as 6.093, etc. As usual, I've put in a token gesture in the direction of a full display and then rounded it on the next line. And that enables me to answer the question in context. So he can climb up 6.09 meters. Well, that ends that study of ladder problems. Do take away the idea that you can make the problem much simpler by using the diagram carefully, and that of course implies that you've drawn it big enough and clear enough to use in that way. So that brings us to the end of this presentation on ladders. The next one is on suspended objects.